All right, so if you are ready, there's number 1 and kind of number 2. I'll scroll a little bit so you can see number 2 better. But yeah, so there's number 1. I think, as long as I push the buttons on the calculator, I think the ultimate answer there is 0.172 centimeters per second for the rate of change of height, or rate of change of depth. I think I might look that over. Should look familiar. We did do a question very similar to this during our related rates unit, and I think one other time since then. Substitution being a bit of a tricky step there. Needs to be done based on the information given. All the steps look good. The only one that I would be concerned about would be that final step with I push the buttons in the calculator. Does anybody else get that 0.172 number? Yes, no? Yes, a couple of people said yes. Okay, good. I usually push the buttons right in the calculator, but as you know, every now and then something inexplicable happens. Do you all have any questions on number 1? You very well might. I'm okay with that. These can be tough questions. I'll just give you a minute to think. You're welcome to write all this stuff down, but realize this is part of a video that will be posted a little later, and so if you actually wanted to watch that, you can do that too. No need to scribble but you're welcome to do that if you want. Nobody's saying anything. Okay, well, let's move on. So let's move on to 2 and 3. There's number 2. And there's number 3. So number 2 looks pretty good for a Riemann sum. And number 3 was a L'Hopital's rule. I ultimately ended up with 0 after all was said and done. Again, kind of like last time when we looked at these, please keep in mind that you have to have what's in the purple box in that format where you evaluated the limit of the numerator and you've evaluated the limit of the denominator separately to show that L'Hopital's rule could actually be used. And then, of course, you use that and you get an answer. Again, I'll just kind of pause for a moment to let you think about questions you might have. Happy to address any of those. It's always exciting for me as a teacher to see growth. And I think about the Riemann sum there. And I think it's pretty natural that when you first, like last week when you first saw those symbols, that all the symbols would be a little bit scary, but I feel like you guys are just motoring through a question like number 2 at this point. Carson, what's up?
So how do you do a derivative of
the integral?
Yeah.
So I'm going to give you a brief answer. The brief answer is, I would suggest checking out the videos posted from last week. We talked about something called FTC2. And there's a quick, very, very quick way to do that. I'm also going to give you a long answer. But Carson, you have to watch the videos, dude. You have to, okay? Because what I'm about to show you is going to be just like a sliver of what you need, okay? You good with that?
So the videos are like on the school, you just...
Yeah. So like let's say you were absent during Unit 5, Day 12, or something like that. Just go to the Unit 5, Day 12 folder, click on it, and there should be a little link that says Video from Today. And that would be, I'm actually making one right now. We're 4 minutes and 52 seconds in. Where I basically just hit record, and then I just record whatever happens, and then I post that. So it's basically the screen and our voices. Should be true of every regular class. Okay, so if you're going to do this, this might actually be an interesting development for the rest of you guys. Check this out. So this is actually going to be, and Carson, the reason why I said you need to watch the videos is because what I'm about to do is not typical. Because typically you're not going to be able to find the antiderivative. But can you all see how finding the antiderivative here wouldn't be that hard? Well, typically that's not going to be the case. So you'd want to use the trick, what we call it the FTC2 trick. Or what's the three-word phrase we use? It's the one that everybody remembers, drop and derive. That's right. So here we go. If I can evaluate that definite integral, the antiderivative of sine is cosine, or excuse me, negative cosine, evaluated from pi to x. And then I continue with FTC1. So this would be negative cosine of x minus negative cosine of pi. Right? So then I get d dx of negative cosine of x plus cosine of pi is negative 1. And as maybe you are seeing here, frankly, if I didn't know my unit circle, is it about to even matter? Aren't I about to do the derivative of whatever that constant is? So it would end up essentially, even if you made a mistake, essentially go away. So d dx of cosine is negative sine, and the negative of negative sine would just be sine. So you get sine of x, the derivative of negative 1 is 0, so you just get sine of x. So
you do the derivative twice?
no, you do the antiderivative. That's what the tall skinny s is. And then you do the derivative. But Carson, listen, you have to believe me. Maybe the rest of you could chime in. Like, can I get a little support here? Carson, you absolutely must watch the video and see the FTC2 trick, because, let me point this out. What I just showed you is not going to work at all if it's this, or something like this. Right? Good luck finding that antiderivative. You're not going to be able to do it. Okay? So you need to know what Joe said. You need to know that drop and derive FTC2 trick. Have to do that. Maybe somebody can help Carson with that, because he needs to know that. You will be one lost puppy without it. Okay. What else? Sorry, I wish I could go back and reteach that entire lesson. I don't have time. I did my best. Okay. Anything else, question-wise? Okay. Good deal. So I know we have RQ6 coming up pretty soon. Has anybody been looking ahead? When is RQ6? Say again? Next Monday, she says. Thursday, Jackson says. You ought to be checking your calendars. RQ6 is coming up soon, okay? So please do. Okay, I'm ready to move on if you are. This would be a bad time for you to just be like, it's Monday, it's first period. I just don't feel like talking yet. Be a good time to say something. All right, fair enough. Okay, so let's see here. Last time we talked about average value. I'm trying to decide how I want to do this. We talked about average value and how that related with definite integrals. We also talked a little bit about that L'Hopital rule that we just did a second ago. And we are going to now today, this is a really, goodness gracious, this is a really important concept. We're going to spend, I think, the next, 3 days on this? Something like that. I think it's next 3 days on this. And this is a more direct, formal application of something we call the net change theorem. This is our first concept of this Unit 6. And here it is. If I could put this in a nutshell, the net change theorem is this. The definite integral of a rate of change gives the net amount of change. So the words rate and amount, we can't just blow right past those and not understand the difference between them. So if I told you that the rate was ice cream cones per minute, what would be the amount that would go with that? Say again?
Ice cream cone.
Number of ice cream cones, right? That would be the amount of ice cream cones. If I told you that the rate was puppies per year, what would be the amount that would go with that? Number of puppies. If I told you the rate was miles per hour, that's the rate, what's the amount that goes along with that? Number of miles. Does that make sense? Bless you. So I've used this example before. If a police officer pulled you over and said, I'm sorry I had to pull you over, you were going 90 miles. Now you have a choice at this point. You could correct the police officer and probably insult them and get worse of a ticket, or you could just do it in your head and think, your rates are all messed up. But you would already know you were probably, instead of being in trouble for going 90 miles, you're in trouble for going 90 miles per hour. So the difference between an amount and a rate is everything, right? And the units tell you that. So today what we're going to do is we're going to take this net change theorem and we're going to apply it to motion, okay? Like velocity and position and acceleration and stuff like that. Okay, so I want you all to consider the meaning of this integral from 0 to 4 of v of t dt. And I want to kind of lead you through, hopefully, what will be some logical thoughts. The first one is this. How does velocity relate to position?
Position is your velocity,
Other way around.
The derivative of position.
Velocity is the derivative of position, yeah. So would you guys be okay if I, just as maybe just a little note here, and you should write this down, I'm going to say that position is modeled by x of t. Eric, could you turn the volume down there? Thanks. Okay, so if position is modeled by x of t, let's see if this makes sense. Couldn't I just rewrite this as the definite integral from 0 to 4 of x prime of t dt? Do you see how I've just like rewritten it? I haven't changed anything other than just like the notation. Okay. Velocity is just the derivative of position. Okay, so then I'm going somewhere with this. Isn't the tall, skinny s mean do an antiderivative? So what's the antiderivative of x prime? It's just x. Okay, now we're getting somewhere. So I'd say this equals x of t evaluated from 0 to 4. Still following? Using just FTC 1 and 2 here, just the full fundamental theorem. Okay, then my final step would actually be this. I'm going to say the definite integral from 0 to 4. And if it's okay with you, I'm going to go back to that v of t notation. Right, I still haven't changed the value or anything like that on the left side. I've just messed around with the notation a little bit. Now on the right side, I'm going to write x of 4 minus x of 0. Right, as I complete that fundamental theorem. And I want to take a second and focus on this right here. X of 4 minus x of 0. What is x of 4? What does that mean?
Position at t equals 4.
Yes, position at t equals 4. And I didn't give you units here, but wouldn't that be measured in like meters or feet or miles or something like that? Okay, then what is the meaning of x of 0?
Initial position.
We'll just say position at
T equals 0.
t equals 0. So it could be the initial position if our time started at 0. But the truth is our time could kind of start anywhere, including even negative times, right? Because negative would just be it happened before we started paying attention, something like that. So we got position at 4, position at t equals 0. So what's the difference between them? Physics people could really help us here. If I've got, to use Hunter's words, if I've got final position minus initial position, it's like more or less what this is, what are we talking about?
Displacement.
Displacement, yes, that is a really good definition. I'm going to put that down, and I'm going to put something else down too. So even if you didn't know that word, which you do need to know that word, couldn't we say that this is the change in position? Change in position, which, as Hunter correctly pointed out, that is the definition of what we call displacement. Change in position, aka displacement. Let's go back to the net change theorem, what I have in the purple box. Purple box says the definite integral, which we had up here, of a rate, and you got to admit, velocity is certainly a rate, is it not? So the definite integral of a rate gives the net amount of change. So if I do the definite integral of velocity, I get the amount of change of my position. Make sense? It's fairly well spelled out up there. So we can come down here, and I do want to use the word that Hunter mentioned. We can say, therefore, the definite integral of velocity is displacement. And I thought it might be fun for us to put a number to this. So off to the right, I have a graph. It's a graph of velocity. And you guys remember I taught you 3 ways to evaluate a definite integral. What are the 3 ways? Somebody name one of them. Area, FTC, or if you have a property, right? And we don't really have any properties here. FTC would be awesome if we had a function for velocity, but we don't. And clearly you can see on the graph I've given you areas, right? Okay, so what do you think the actual numerical value of that definite integral is? 2.25, let's see here. Wouldn't it be positive 3 minus 1 plus 0.75 minus 0.5? So I haven't checked the numbers out here. Let's find out. So it'd be 2.25, you said? Yeah, I agree. So this would equal 2.25. And again, the units on something like that would be meters or feet or inches or miles or whatever linear unit of travel we've got. Okay, so the definite integral of a rate of change gives the net amount of change. So what do y'all think? And we just applied that to velocity and displacement. You good? Okay, so this might go a little bit easier for you. I'm going to be a little less symbolic heavy on this one. I think you'll see for relatively obvious reasons. So let's take a look at this next one. You can see that this is obviously related to what we just did, but it's different. And I'm not going to go through that development because the development of this would be a little bit of a mess because of what set of symbols? Absolute value make this a big mess. So I'm hoping that what we just did will inform what we're about to do. So you got to admit this is potentially very different from what we just did, although similar ideas, but end result very different. So this is the definite integral of the absolute value of velocity. And again, physics people, I don't know if you know this. What's the absolute value of velocity? Like, what's another term we'd use for this?
Total distance.
No, you're talking about the full answer. I'm just talking about the absolute value of velocity. Speed. So before we did the definite integral of velocity and we got displacement, so let's jump down here to the bottom. Does anybody know what the definite integral of the absolute value of velocity is? I think you said it. Total distance traveled. That's right. So I'll put that whole phrase up here. Total distance traveled. Let's examine why that would be. Anybody notice, and this is the same velocity that we had up on the first example, what does the absolute value do to the velocity graph? Yeah, do you see how there was 2 loops that were below the x-axis or the t-axis before, and now they've been reflected up? Okay, so everything's above the t-axis now as far as the loops and turns and all that of the graph. So when I try to evaluate this definite integral, wouldn't I get 3 plus 1 plus 0.75 plus 0.25? We'd have all positive accumulation, wouldn't we? Plus 0.5, sorry. I somehow messed up that last area. I think I was thinking one step ahead. Yes, I was. Okay, anyways, now the numbers are right. So this would give me, what, 5.25? Okay, so 5.25, that's very different. So why would this be total distance traveled? You guys know on your car, you obviously have your speedometer. You ever notice the odometer? What does the odometer measure? Total distance traveled, that's right. So think about it like this. If your odometer, instead of being an odometer, was like a displacement-ometer, how could you make your displacement-ometer 0?
As far as you drive forward, you drive reverse.
Yeah, or like, let's be really literal about this. How could you get that displacement-ometer to be exactly 0? Go to where the car was built. Just drive your car to wherever the car was built, and the displacement-ometer would be 0, would it not? Now, the odometer would continue to accumulate positive mileage, right? Because we're concerned about what Merrick said, the total distance traveled. It's the more important measurement. And so we're going to be able to use both, right? Displacement will matter, total distance traveled will matter. Can I ask you another question? What was the answer for the first one again? Was it 2.25? And this is 5.25? The fact that those two numbers are different, the fact that displacement is different than total distance traveled, what does that tell you about how the particle was moving? If the total distance traveled is different than displacement, what does that mean? Say again? Okay, the object traveled in a negative direction. We're getting there. And it had to change direction. So not only did it travel in a negative direction, didn't have to be at least one time when it traveled in a positive direction too. And if it traveled in a negative direction at one point and a positive direction at another point, it had to change direction. That make sense? Okay, good deal. So get your calculators out. You guys are going to learn, if you haven't already learned about it, a new calculator function here. And so our first two examples here, are very much, can you just apply the two things you just learned? Okay? And C is a little bit of an extension of that. And up here on the screen you can see I asked, hey, what's the displacement of the particle on the interval from 1 to 5? And then I say use Math 9. I would just encourage you on your calculator, push Math, push 9, and see what shows up. And I'd be willing to bet that you're able to figure out how to use it. If you haven't already seen this, it's lovely, right? So cool. Okay, so please give it a shot. See what you can do with number 1, A and B. And I'm hoping you can get through A and B pretty quickly. And please try C. C, I don't know. Hopefully you can do C. We'll find out. Instead of writing all this out, you can just put VO2. Totally okay with that as long as either you or the question is labeled it as such, just put VOT in. Same thing, please. So for your integrand, I love what you did here. This makes a lot of sense. I would just go VOT for that. Okay, I want to look at these first two with you all. Very weird. So, A. So did you all get like negative 135 point something? Okay. So let me give you an example of something that would earn no credit at all on some quiz. They get the decimal right? Oh, sorry. Did they get the decimal right? So if you wrote that, you get nothing. I'm not joking. Even if you put feet, which would be the correct units for that number, you still get nothing. Explain why? You didn't show anything at all about how you got it. So here's all you got to do to fix it. Write the definite integral from 1 to 5 of v of t dt equals, and now you get full credit. So please note, we refer to that as a bald answer, like you didn't show any supporting writing at all. And listen, I know what Math 9 is. You now know what Math 9 is, and it's awesome, right? It's so convenient. And if the calculator's active, that's exactly what you ought to do, but you have to write down the setup. You have to write down in regular old math notation with the tall, skinny s and everything, the setup. And to be honest with you, I hope, to goodness sake, that that's all you'd write on Part A. I hope that you would not write anything other than exactly that. Anything else is a complete waste of time on a quiz or a test, and possibly something that might mess you up and cause you to get the wrong answer. Part B would just be the definite integral from 1 to 5 of the absolute value of v of t dt. And here, I think, did you guys just get positive 135? Okay, so this is a nice contrast to the one we did just a second ago. So the one we did a second ago, the displacement and the total distance traveled were different. And Isabel said that means that the particle turned around, right? The object turned around. So here, the total distance traveled is positive 135 and the displacement was negative 135. What does that mean? Never turned around, and it was going backwards the whole time. That's right. It's going backwards the whole time, and it never turned around. Just kept on going. Okay. So Part C. Did anybody try Part C? Okay. Let's see how you did. So with Part C, it says if the particle is at position x equals 4 when t equals 1, what is the position of the particle at t equals 5? I would like to show you all this. If I am looking for the position at t equals 5, would you be okay if I translated that as this? I'm looking for, I'm trying to find x of 5, right? So the position x equals 4 when t equals 1. I'm looking for position at 5. We could think of that as x of 5. So here's how I would start off. I really like using FTC here, although there's other ways to do this notationally, but it really is still FTC. I would say the definite integral from 1 to 5 of v of t dt. I'm going to start there. Why in the world would I pick t equals 1 for one of my limits of integration? I know that one. That's right, Cole. That's one that I know. Why would my other limit of integration be 5? I'm trying to find that one. Does that make sense? So remember, with your limits of integration like this, one of them needs to be the one that you already know, and the other one needs to be the one that you're trying to find. Integral from 1 to 5. And then why would I do the antiderivative of v of t? Say, yeah, that's how I can get position. That's right. Here's what I would say. This equals x of 5 minus x of 1. I'm just using FTC, or really the net change theorem. The definite integral of a rate gives me the amount of change. Okay, so then on the right side, x of 5 is my objective. X of 1, I know, is 4. And then thankfully from my work in A and B, I already know the value of the left side, right? Isn't it negative 135? So it'd be negative 135.028. So that's my displacement. I'm trying to find x of 5. So how do I get x of 5 by itself?
Add 4.
Add 4. That's right. So if I add 4 to both sides, I get negative 131.028 equals x of 5. I'm done.
Is that all the work you have to show?
Yeah, I think that's... Now, so I'm presupposing that you notice... Yeah, I mean, really, honestly, yeah. That's all you got to show.
Well, you have to show all that.
Do I have to show what?
All of that.
So let's see here. What is it that you do and don't need to show? So I would want to see this for sure in the box. But then if all you showed after that was that, I'm okay with that. Because really, what's going on between those two steps? Like you added 4 to both sides. Do you really need to show that? I personally don't think so. But I obviously want to see your answer, and I would definitely want to see this add up.
So what if you just do it like visually, where do you know that 4 is the initial position, and then you just do the integral, which gives you the total distance traveled, and then you just subtract initial minus distance traveled?
Well, it would be...
Or I might have mixed up the order of what I said.
Right. So what are you proposing that you would actually be writing? That's the key thing. What are you telling me that you would write?
4 minus the integral of 1 to 5 dt.
How that's to be honest with you, that's really no different than this. You just rearranged it slightly, right?
Well, I don't.
Slight rearrangement.
Oh, okay.
So I'm assuming that you would write what you just said and then answer. I'm good. So your steps have to involve a definite integral. I don't see how you could get around that. But if you had it like slightly rearranged, or you already added the x of 1 to both sides or something like that, and maybe you just said it's 4 and you added it to both sides, I'm totally okay with that.
So you don't have to have like the x equation.
No, you got to have x of 5 in there somewhere. But yeah. That's a good question. But I think we're speaking the same language. I think your ideas are really, really good. Let me just show you the setup for this last one. And then I think you can figure out how you could use Math 9 to help you with that. So check this out. Notice that it asks you to find f of 6, but then in the end it gives you information about f prime. So if it gives you f prime but wants to know about f, what are you going to have to do? That's right. So check this out. I'll do integral from 1 to 6 of f prime. Why would I pick the 1?
Because that's you're given there.
I know that one. Why would I pick the 6?
Because that's what you're given.
That's right. So this would just be f of 6. Now to kind of use Carson's idea, couldn't I just use f of 6 minus 3? And then I would go 3 plus this definite integral. How in the world am I supposed to find the definite integral of root log x? Math 9. So you would just use Math 9 plus 3, and you'd be done. Okay? I don't know what the answer is to that one. Maybe I'll do that real quick before we go. Say again?
6.421.
Say one more time.
6.421 was the answer.
So he says 6.421. We're going to give all the... Is it RHYS? Going to give all that credit to Reese because he apparently did that. Awesome. Thank you. Guys, have a great rest of your day. Look forward to seeing you mañana. We'll keep talking about the net change theorem.